So thanks for the introduction. Good morning, everyone. I'm Saidur from Ewha Women's University. So I'm so excited to present our work on the DeepCoFFEA, improved flow correlation attacks on total via matrix learning and amplification. So this work is a joint work with University of Minnesota and RIT. So the majority of the work had been done while I'm in Minnesota. Right, so Tor. So Tor is one of the most popular protections against surveillance with millions of daily users. Then what is Tor? So instead of directly communicating with web server, the Tor uses multiple hops to connect to the server. So we can hide our identity and destination. So in theory, there should be no way to trace a specific Tor connection back to the user. So no user identifiable information is left in both client and server side. However, still we can monitor the egress and ingress of the Tor traffic, and we can correlate them based on some traffic pattern. So this can be achievable by the network level adversaries, such as the internet service providers and governments, or like AS level the adversary. So this is called end-to-end flow correlation. So let me show some specific traffic pattern. So here we draw some scatter plot about the connections going to the different destinations, such as Google, Naver, and YouTube. So you can see the sequence of the TCP packet sizes and packet timings. And as shown, the traffic pattern going to the different connections exposes some unique pattern. So the adversary can leverage this to correlate the different both ends of the total connection. Right, then let me introduce some more specific attack scenario of the flow correlation. So here we have an agent, which is the global level adversary. And he is the machine learning expert, and he is interested in answering the specific question, investigating whether or not a specific person who is Bob is dissident. So with this question, the adversary creates his training database. So what it does is he monitors the bunch of total connections and put the pair of the inflow and outflow and label them 1 if they are correlated, 0 otherwise. So using his training database, he trained a model to run the correlation between these pairs. So now his model is ready. So he monitored both ends of the total connections. Let's say the 1,000 connections, which includes the Bob's connection. So eventually, using this 1,000 connections, he put the pairwise combination features of inflow and outflow. So in total, he has the 10 to the 6 flow pairs and feed it to the model. And the model returns 1 if they are correlated and 0 otherwise. In this way, he can answer his question, so which exposes the Bob visit the specific some website, which exposes his political leaning, so which is really bad. Right. Then let me spend some more time what problems we can notice in the methodology obtained by this agent. So first, the recent literature of flow correlation shows pretty nice performance with high accuracy. But the problem is it required to put n squared flow pairwise combination of each flow, so to investigate n connections, which is really expensive. So this results in the quadratic complexity. And here is another problem which makes the situation even worse. So this pairwise setting leads to a very low base rate. So why this can be the problem? So let's say we have 1,000 connections and we have one correlator which can detect the correlation with 100% true positive rate and 1% false positive rate. Then let me ask one question. Then can you say it's a good correlator? So my answer is no. So what's happening here? So each inflow will be compared to the 1,000 outflows. So we know the right pair, right answer is the only one, which is green flow here. So with 100% true positive rate, this correlator can correctly detect its right pair, which is green flow here. Also with 1% false positive rate, which means it can misclassify 10 orange outflows as positive, so which are false positives. So which means remaining 989 flows are all negatives. So that being said, the actual success rate will be 1/11, so which is pretty low. Right, so when n increases, so number of connections I'm investigating, so when this n increases, the success rate will be approaching to 0. So such a pairwise setting, such a pairwise-based learning makes the feasibility of the flow correlation much harder. So the correlator should achieve very low first positive rate to show its potential. So based on this observation, our research aims 2 goals. So first, develop a good deep learning architecture, which requires a linear complexity. And second, use summer methodology to exponentially reduce the first positive rate. So here we propose deep correlated flow feature extraction and amplification, in short, DeepCoFFEA. So our attack is never ever related to coffee, but you can pronounce it as a DeepCoFFEA. So here we propose our deep learning model, which consists of anchor and positive and negative networks. So positive and negative networks share their weights. So let's say that Davis inflow goes to anchor network, and Davis outflow goes to positive network. And all other people's outflows, which is not David, go to the negative networks. So in this way, we can achieve 2 separate embedding, so one for inflow and the other for the outflow. And 3 different networks are jointly trained using the triplet loss. So our triplet loss actually maximizes the correlation between correlated pairs and minimizing the similarity between uncorrelated pairs. So when the learning process, the embedding of the Davis inflow becomes closer to the embedding of the Davis outflow. So likewise, our network, our model generates cosine similar embedding if inflow and outflow are in the same connection. Then how this network, this model requires only n triplets, so linear complexity. So the key is how to select the negative samples. So instead of feeding all other people's outflows into the negative samples, here we select the most effective the negative sample. So how we can do this? So here, let's say we have Davis inflow and Davis outflow, which is the positive here, P. And we select 1 negative samples, which is far away from the positive, but with the alpha margin. So we set some boundary, and we found this alpha, using the bunch of experiments. So in this way, this network only requires, the n triplets, so complexity will not quadratically increase depending on the n, which is the number of connections. Right, the next problem, how we can reduce the first positive rate. So amplification is adopted by the randomized algorithm. So the good example could be, like the coin toss. So let's say if the coin falls on head, then we win. So the probability that the head doesn't fall on, let's say it's the epsilon. Then how can you reduce this epsilon? So maybe the naive approach could be we can just toss the coin, like the multiple times k times. So the failure rate will decrease, like exponentially, because we pick the majority vote over the multiple trials as a final score. So in this way, we can reduce the failure rate substantially. Then how we can use this concept to our flow correlation study? So we can divide each trace, each flow into the multiple subflows. But here we allow some overlapping. So divide the flow into multiple subflows and evaluate our embedding network multiple times. So with this idea, here finally we propose a novel evaluation framework with the separate embedding and amplification. So here first we generate feature embedding. So using the multiple subflow pairs, we generate different each the embedding. And then we compute the pairwise cosine similarity. And if this score, similarity score, is greater than tau, so tau is some threshold we empirically chose. So if it's greater than threshold, we can say this pair is correlated, so which is 1 here, otherwise the 0. So after that, we take the majority vote. So we use the 9 out of 11 for the final result. So eventually, if the pair gets the more than 9 1 votes, that means that pair is the correlated. So in this way, our approach of the amplification substantially reduces the first positive rate from 12% to 0.13%. Also, in turn, our ROC of DeepCoFFEA clearly outperformed the state-of-the-art, which is deep core with substantial significant margin. And this is not the end. So our network actually only requires n triplets. So this leads to the substantial evaluation cost. So more specific, 2 orders of magnitude faster than the state-of-the-art. So likewise, we can achieve the substantial improvement against the state-of-the-art in both complexity and the performance. And anything else? Yeah, so we explored a variety of experimental scenarios, but here I only introduced the 2 different experiments. So we further evaluated DeepCoFFEA against the defenses, including phosphor to transport and website fingerprinting defenses, including the WTF pad and the front. We also evaluated DeepCoFFEA against some time-separate testing data, so up to the 3 years apart. So, like as shown in the left figure, the DeepCoFFEA still performed adequately against the defenses. Also, it performed very nicely against the time-separate testing data up to the 14 months apart. So, what we learned here is the correlation appeared to remain between the total and exit flows even against the defenses and time gap data, which DeepCoFFEA successfully detects. So for other experiments, you can check in the paper. Right, so the future work. So first, so even though we follow the data methodology, data collection methodology adopted by the deep core using the SOX proxy to collect the exit flow, but we thought that this can possibly bring up some artifacts on the traffic. So evaluating DeepCoFFEA against more realistic data, so better data, is the reasonable next step. And second, recently researchers, including me, have worked on the data-limited fingerprinting or traffic analysis using more advanced deep learning architecture. So like how to incorporate such network into the flow correlation study could be some interesting next step as well. And third, our evaluation framework actually doesn't fully support, doesn't yield perfect linear complexity because we do the pairwise cosine similarity computation at some point. So the remaining question is how we can build the loss function as well as the network architecture to fully support such the ON evaluation. And last but not least, the most important next step could be the designing the effective defenses against the DeepCoFFEA style of the attack because existing defenses show seems to not that robust to defeat the DeepCoFFEA. Right. So thanks for your attention, and I'm happy to take any questions at this point.
If you have questions, please come up to the microphone. In the meantime, I'm curious how you actually divide flows into windows. Is this something that you do after you've collected the observations, or is this something that you need to do while you're collecting the observations? So for example, do you need an active attacker to start creating spacing to create these windows, or do you just collect the data set and then you find the windows?
Yeah, I mean, that's a good question. So we divide the windows, these partitions after the collection, but I agree that like the later approach might be more interesting, setting. We may try, yeah.
Okay, I have another question. Is there a reason why you chose to pick cosine similarity instead of other distance metrics?
So yeah, that's also a good question. So we empirically choose the cosine similarity because that works better than other distance metrics. Yeah.
And one final question for me. Do you know of any defenses that Tor could deploy to actually prevent this attack? Because it looks like most of the defenses out there were not doing very well against your attack.
Right. So in the paper, you can check in more details about such defense-based, like evaluation. So actually, we came up with our own defense, which is more focusing on, this DeepCoFFEA style attack. Because DeepCoFFEA, the main, the main feature is the amplification. So we found that window level obfuscation works slightly better than other defenses. But this is very beginning stages. So, but yeah, we will keep, keep working on to make it solid. Yeah.
Okay. Thank you so much.
Yep. Thanks.